Hello, I'm HaRim Jeong. I major in optics and photonics at Yonsei University. Let me start my final presentation. There are four sections. At first, I will explain Fraunhofer diffraction theory briefly because I have done it several times before, and I will explain solutions for problem 4.9 with MATLAB, code, and movies. And then I will explain imaging system of coherence and incoherent light. At last, I will explain solution for problem 6.3 with MATLAB and some movies. Fraunhofer diffraction is come from Fresnel integral. Equation 4.17 is Fresnel integral if g is much larger than k dot cushy square plus eta square over 2, then quadratic phase vector goes 1, and then Fresnel integral becomes this last equation. This is Fraunhofer diffraction. Fraunhofer diffraction is proportional to Fourier transformation of u cushy eta, so we can calculate diffraction pattern by using Fourier transformation easily. Second section is a solution for problem 4.9 with MATLAB. Find an expression for the intensity distribution in the Fraunhofer diffraction pattern of the aperture shown in figure 4.19. Assume unit amplitude normally instant plane wave illumination. The aperture is square and has a square central obscuration. We can obtain Fraunhofer diffraction pattern by Fourier transformation of aperture. The aperture can be expressed as subtraction of two rectangular functions. And Fourier transformation of rectangular function is sinc function. So Fraunhofer diffraction pattern in image plane is this, and intensity of Fraunhofer diffraction is whole square of this amplitude. The result is the last equation. This is expression for the intensity distribution in the Fraunhofer diffraction pattern of the aperture. And I proceed with this process to the MATLAB. And here's the MATLAB codes. First, I defined grid and constant and made the aperture by subtraction of two rectangular apertures. I set the wavelengths to 600 nanometer and set WO and WI to 1 millimeter and half millimeter. And then I Fourier transform aperture with MATLAB code with FFT. And next I multiply phase terms to the result of FFT and divide by square of I lambda z. Finally, plot the result with MATLAB code. And I tried to plot the intensity distribution function directly. And this is the movie as Wi close to WO. Third section is imaging system of coherent and incoherent light. By the Abbe theory, high frequency light is limited by finite pupil, so the image is not perfect. Amplitude Ui is represented by a superposition integral where h is the amplitude in response to a point source object. And the light amplitude about the ideal image point is simply the Fraunhofer diffraction pattern of the axial pupil. So point spread function h can be represented as last equation by replace replace M Cauchy and N eta with U and V. Two types of illuminations can be considered. One is coherent light and the other is incoherent light. Coherent imaging system is linear in complex amplitude. An incoherent imaging system is linear in intensity. So the intensity distribution function can be represented by these two equations at each cases. In case of coherent system, the amplitude transfer function ATF capital H function is defined as the Fourier transform of the amplitude impulse response small HUV function. And also ATF can be represented as Fourier transformation of the pupil function. An incoherent imaging system is linear in intensity. Normalized transfer function defined by this equation. Numerator of this equation is Fourier transformation of h square, and with Rayleigh's theorem, OTF can be represented by third equation. And then if we replace P and Q by P prime minus Fx over 2 and Q prime minus Fy over 2, we can get the fact that the OTF is the normalization autocorrelation function of the ATF. The numerator represents the area of overlap of two displaced pupil functions. So OTF can be obtained by calculating the ratio of area of overlap and total area of pupil. Section 4 is solving problem 6.3 with matlab. In this case, the aperture is same with problem 4.9, but the light is partially incoherent. And we have to obtain optical transfer function in various cases, with and without the star present, and the size of the star approaches the size of the pure pupil. I set grid and constant, and I make aperture like I have already done in problem 4.9. I set the wavelengths to 600 nanometer and set W to 1 millimeter, as same as before. This part is summation of total aperture area to obtain a ratio later. Next line is set initial value of OTF. From third line to end is first sentence to shift aperture area to obtain ratio 1 by 1. Middle of first sentence includes getting ratio of overlap area and aperture area, and also plotting aperture and OTF. This is cross-section of the optical transfer function without the star present. The OTF cannot exceed 1 because OTF is the ratio of overlap area and the initial pupil area. And cutoff frequency is 2f0 in OTF cases, in incoherent cases. This is cross-section of the optical transfer function with the star present. The optical transfer function when the size of star approaches the size of the few pupils. Side peak values is a quarter because the overlap area ratio is a quarter when first met. This is the process of changing OTF as the star approaches the size of the few pupils. The middle of OTF is always 1 because it overlaps exactly at point 0.0. This is a graph of OTF for all points, not just the x-axis or y-axis. I used two for sentence to calculate the overlap area for all points. Thank you for watching.